Hello friends. Now we are supposed to be studying interrupts, how to configure, how to use, where to use, why to use, and make the operations very efficient. But before doing that, I want to tidy up this program. As you can see here, you have looking at line number 22, from 22 up to the line 30, what we have done is we have tried to configure the IO ports. Let us make it more neat. For example, here you have initialized and configured UART, and for that you have written a small function. In the same way, for this also we will have a small function, so the program will look very neat. So how to do it? I start with this, I select all this, and I cut it, Control X. Thereafter what I do, I say I'm going to create a program, a function. Let us give it a name. Now you will also see in the process how to name the functions and how to use them and so on. Let us give it a name IO underscore init. Init means initialization. It is a short form of init. So we have again void. Void means I am not going to give it any parameters. That's why we call it void. And it is not returning anything directly into any variable, therefore it is void here also. Look at line 52, it is void, and towards the end again it's void. This second void means that I am not going to give it any parameters on which it will work, and this first void means it is not going to return any value to any variable after the program has been executed. Whatever values come or assigned, they go into the variables which are already inside the program that you will see now. Then you have to give a brace, then another brace, and in between you need to write the program. What we have done is we have already cut a part of the program to be brought to this location, line number 54. So let us do it. Control V. So I have copied it. So that part has come here. So the space at the top has become cleaner. Now I will copy this line. Look at line number 51. It is not mandatory, but it gives it a better readability. Oh, what happened? Let me do it again. So this line, this looks like a separator and it gives better readability. So I have Control V. So I have separated this function void IO init from UART init and things which are at the top, which is the delay. Now what has happened here? This is the name of the function, and Control C, I will tell you why, and I will copy this. What has happened? Some key has malfunctioned. Now this is the function. I'm going to use this function. This is the description or definition of the function. Whenever IO init is called, this will get executed whenever IO init is called, but it has to be called. So let us call it. Call it means what do you do? Control C. Where do I call it? Before I call it, I must tell the compiler that look, I have a new function. Control V. This is called prototype. This is the prototype of the function, and what we have written here is the actual definition of the function. This one, IO. And now how to call it? Just copy this. Control C. Where it was originally everything was here. So let me call it here. Control V. Then close the bracket. So as soon as this is executed, it is actually going to shift control to this place, to 52, and execute it and come back. What is the sequence? Let us see it again. When the program starts running, it really starts from line number 20, which is the first instruction under main. Main is where the program starts. So in the main, this is the first instruction at line number 20. So it will assign 60,000 to C, it will assign 1 to B, and then it will say, I want to run IO init. So as soon as you execute line number 20, it is going to move to this. Then it will execute this whole function. After executing this function, that is all these instructions, it will execute. And after executing, it will come back to the point where it had left. It has implemented this. It has run this program. It has run this program at line number 22. So now it will come, after executing this, it will come to line number 24 and it will execute UART init. So when this is executed, when this instruction set is executed, what it will do? It will go to UART init, which is this. And when it does that, it will execute these things. It will execute all this, and after it sees this brace, it will go back to where it had come from. It had come from here, UART init. After executing this, it will come to line number 25. Like this, the control moves. So this now looks a little better than what we had earlier. Now you can see it has become small. So instead of several steps here, now you have just a few steps. Even this, C equal to 60,000, B equal to 1, and this, all this can go into another function called init, initialization overall. But we are not going to do it right away, we will do it later. Now this is no more required. It was a jumble, therefore I had put it here. This was just to isolate UART from other things. So this I will remove, and then after doing this much initialization, it will execute all this. I have added a function enable interrupts. Without this, it cannot handle interrupts, right? So in our original program, this is not there, it is like this. But when we start implementing interrupt, we will remove these comments, and so it will become active. Now, what about the remaining things? Fine. So now how many functions we have? We have delay function at line number 45. We have init function, IO init at line number 50. And at line number 63, we have function called UART init. This is all initialization. And here we have a comms function. So we have already seen how this function works without interrupt. This is how it has gone. And remember, you have given void IO init void. This is called the prototype, and now your program is more neat. Subsequently, we will change these variables A, B, E, alpha, C, D, etc. because these letters themselves don't say anything about the purpose of this variable. So the name of a variable should carry a meaning or a hint towards the objective of that letter or a variable. So these are all variables. They should be more meaningfully named. See, human beings are not called ABCD. They are given specific names, and from that you come to know many things, like whether he is a Christian or whether he is a Hindu, etc. So but here we are not talking about all those things, conceptual things. We are talking about using something for a purpose. For example, here IO init, this is a name, not a variable, a function name, but nevertheless it is a name, and this can tell us that, well, something is going to happen to IOs, And what is going to happen in it? It means initialization. So it gives a hint that this function has something to do with initialization of IO ports, right? So subsequently we'll change this A, B, E, alpha, CD, etc. And we come back to the bottom here. Yes, all this. Yeah, so it is better. And now, before proceeding further, you think that handling a key is a simple job. Yes, you press a key and something happens, logic 1 becomes logic 0 and so on. And so it is all very straightforward and simple, but it is not so. That we'll see now, because we want to handle interrupts. So interrupts on IO ports, interrupts on UART. So therefore we should first understand why we are going to need an interrupt, or how these devices, these functionalities occur. Okay. So I come here. Well, this is schematics. This you have seen, and I'm going to talk about this particular key. And there are, remember, there are many keys from PD3, PD2, PC3, PC4, PC5, PC6, PC7. They are all connected to this kind of keys, right? So this key we are going to talk about. Let us see how it works. You feel that when you press the key, this becomes 0. It is correct to one extent. But there is something more to it that we will see now. So what do you expect when you press this key? When you press this key, this point is connected to ground, which means it becomes 0 volts. If you look at the waveforms, this is the point, this is the instant of time when you have pressed the key, and therefore you expect that the voltage level will become 0. When the key is not pressed, Vout is connected through this resistance to 5 volts. And since negligible current is flowing, therefore potential drop here, voltage drop here is practically 0, and therefore whatever is the voltage here, the same voltage will occur at Vout. So before you press this key, the voltage level is 5 volts here, and when you press the key, it falls to 0. This is what you expect. But you expect this as you press and hold the key. But what happens? But you get this key bounce phenomenon. When you press the key, you feel that it has closed, and therefore it has come to, from 5 volts it has come to 0 volts. But it is not so. Just as a ball, when you drop on the floor, it keeps bouncing up and down, up and down. In the same way, when you press a key, the contacts close and open for some time, something like 15 to 20 or sometimes 50 milliseconds. So it goes on for some time. And therefore, instead of one key closure, your system will feel that it has got several key closures, and it will respond to each key closure. Are you following this? So instead of one key closure, your system will see so many key closures, and therefore whatever it does for one key closure, it will keep doing for all these key closures. So when you really wanted to press key once, it feels that you have pressed the key 4 times in this particular case. And so it will do something which is not our intention. So how to handle this situation? To handle this situation, we connect a capacitor here. So when you connect this capacitor here, what happens? Initially, key is not pressed. This voltage is 5 volts. This quickly charges the capacitor, and this voltage becomes 5 volts. It will remain in 5 volts. As soon as you press the key, this capacitor will discharge like this, and the voltage will become 0. So it takes some time to discharge. As you can see, this red line is taking some time to reach 0 level. Then what happens? When this happens, when it bounces means actually these 2 points don't remain shorted. That is the meaning of bounce. It has hit it, and without your notice it has gone back, and therefore you get 5 volts here. But the capacitor is already fully discharged, so capacitor will take time to charge up. So capacitor will take time to charge up here. See, this is how capacitor takes time to charge up. Depending upon RC time constant, it will go to a certain voltage level up to this, and we ensure that this voltage level to which capacitor gets charged is less than logic 0. This is logic 0. This dotted line shows the logic 0 level. So as long as the capacitor is not able to charge beyond logic 0 level, the system will assume, you will see it as logic 0. So it will not respond to this closure because it has remained 0 all along. Again it closes, so it discharges. Again it becomes open, so it charges up. So it charges and discharges, but all the time the level of voltage across capacitor remains below logic 0. So it will feel that the switch has closed here, and all along it will find 0, and after some time that bounce phenomenon will disappear and you will actually get 0. So this bouncing phenomenon happens for a few milliseconds only. So we have to carefully select the value of C so that the capacitor does not charge above logic 1 level. It has to remain not even in active region, it has to remain below logic 0. If the value of C is increased, as you go on increasing it, it will take longer and longer time. It is good for us. But if the value of C is small, then RC time constant will be small, and this may rise faster. This may rise very fast, quite possible. From here it will go like this, and it will cross logic 1 level, and when the bounce happens again, it will come down to 0, and then this will be treated as another key closure, which we don't want. Therefore, value of C should not be very small. So what you will do, not very small, not very large. So you have to be very careful in selecting RC time constant. This is what I wanted to tell you now. So you understood? Now when you want to use a capacitor, there is one of the ways you may use a capacitor. You may also use interrupts. What we do with a capacitor can also be done with the help of a timer. So as soon as the microcontroller sees a logic 0 happening for the first time, it may start a timer, say a 50 millisecond timer, and as long as the timer is running, that 50 millisecond delay is running, during that period it will not look at the key at all. So you may keep bouncing from 1 to 0, 1 to 0, it may go on happening, but it will ignore it until the timer has timed out. That is precisely what the capacitor is doing. So either you use a capacitor or you use a timer and use timer interrupt. There's another way of doing it. There is yet another way of looking at it. An interrupt can be generated when this key is pressed, right? And that interrupt there is a choice for you. That interrupt will occur when it goes from 1 to 0. It may occur when it goes from 1 to 0 and remains at 0. It will occur when it goes from 0 to 1 and remains at the top. That is at logic 1. So all possibilities exist. You can select, you can choose. That is called configuring the interrupt of the IO port. So you may say that, okay, when it falls, then I will generate an interrupt and respond to that interrupt. And what is your response to that interrupt? Whatever action you are supposed to take, you will take that action. And at the same time, you will start a timer if you are not using a capacitor, or it will remain 0 for some time. Like in this case, as you have seen, it has gone to 0 and remain below the logic 0 label in the second diagram, as you see. It remains here. So either you use a timer, as soon as this IO port interrupt comes, you can start a timer. So friends, we'll have a look at it again while we actually understand the interrupts. There is one more thing I wanted to tell you about the serial communication. We already understood this, and the configuration was one start bit, 8 data bits, no parity bits, and one stop bit. Here you have parity bit also included. So when you wanted to send 1, 2, 3, 4, 5, 6, 7, 8 bits, you actually send 1, 2, and 3 extra bits. So in all you sent 11 bits. In this case, you are sending only 10 bits. These are the 8 data bits, then there is a stop bit and a start bit. So 8 plus 1 plus 1, that is 10 bits. So this is how we are going to send data. Here you also, to recap, here you will also see that the data is this 0, 1, 1, 0, 1, 0, 1, 1 in this case. But what really happens is you send this one, you are looking at it, you see this one goes here or here maybe, then this one goes here, then this 0 goes here, then it sends this 0 like this one, then 0, then 1, 1, 0, then 1, 1, 0, it goes like this. So LSB is sent first and at the end is sent MSB. You have a right to select this format. One start bit here, 8 data bits, 1, 2, 3, 4, 5, 6, 7, 8, and one stop bit. There is no parity bit, right? This is the other thing I wanted to tell you. So right now I will go back to this, and we have made some changes here. The idea behind this was to make certain things clear, that is, help you learn the C language. So how to reorganize, how to organize our programs and so on. I will stop here and we will look into the interrupts in the next lecture. Thank you, and keep looking into this program. Try to understand whatever I have discussed. You may contact me or you may rerun the program, right? Thank you. Till we meet next. Thanks.